I want you to imagine opening a dusty family photo album. You're flipping to the very first page, and you're fully expecting to see typical baby pictures, right?
Right, tiny, fragile infants.
Exactly. But instead, you turn the page, and you're just confronted with a bunch of fully developed, heavily muscled Olympic bodybuilders.
Oh, wow. Yeah, that would definitely be a shock.
Right. It's this bizarre, jarring, structural paradox.
Yeah.
If you're looking at the very beginning of a timeline, the things you see should logically be in their infancy.
Yeah, they shouldn't be fully formed yet.
Exactly. And that bizarre mental image, that dissonance, is actually the exact dilemma that recently confronted the entire global astrophysics community.
It really was a massive crisis for a minute there.
So welcome to today's deep dive. We are jumping into a fascinating NASA article detailing some recent findings from the James Webb Space Telescope, which we'll just call JWST for short.
Yeah, that's much easier to say.
For sure. So our mission for this deep dive is to explore a really specific cosmic mystery. Basically, did JWST just completely break our entire understanding of the universe? Or were these early galaxies just playing a massive trick on us?
And to really get why this matters, we have to talk about what astronomers actually expected to see out there. Because, JWST is effectively a time machine.
Because light takes time to travel.
Right, exactly. So looking at things billions of light years away means we're seeing them as they were billions of years ago.
Right, near the dawn of the universe.
Yeah, within just a few 100 million years of the Big Bang. And at that stage, astronomers totally expected to see what you could call galactic pipsqueaks.
Galactic pipsqueaks, I like that.
Just these tiny, loosely bound clusters of stars that would eventually, over billions of years, merge and grow.
But that is not what JWST saw when it sent back those first deep field images, is it?
No, not at all. Instead of pipsqueaks, it found galaxies that appeared to have grown so massive, so fast, that literally no computer simulation could account for them.
And this is where we get to the real crisis in cosmology. Because, if these early galaxies really were that huge, that early on, it meant the standard model of cosmology might be completely wrong.
Yeah, the lambda CDM model. It's the fundamental theory that explains, what the universe is made of and how it evolved.
Okay, let's unpack this for a second so you, the listener, can really picture it. It's like digging at an archaeological site, right? And finding a fully built, modern skyscraper in a time period where only mud huts should exist.
That's a great way to put it.
If you see that skyscraper, you basically have to question everything you thought you knew about history.
You do. But, and this is a big but, as Stephen Finkelstein pointed out, he's a professor at UT Austin and a co-author of this study we're looking at, you can't just throw out a foundational theory overnight.
Right, because the standard model has stood the test of time for decades.
Exactly. It requires overwhelming evidence to toss something like that out. So researchers had to stop and ask, okay, is the universe broken, or is our measurement of these galaxies just fundamentally flawed somehow?
Which perfectly sets up the central mystery. If the standard model isn't broken, then what on earth were we actually looking at through that telescope?
Well, the answer comes from a really brilliant breakthrough study published in the Astronomical Journal.
Oh, right, the one led by Katherine Shrabowski, the grad student at UT Austin.
Yes. She and her team were using data from the Sears survey, that's the Cosmic Evolution Early Release Science Survey, and they figured it out. These massive galaxies aren't actually that massive at all.
Wait, really? So what are they?
They're just wearing a really brilliant disguise.
Okay, wait. I need to push back on this a bit. The article mentions that black holes are what's making these galaxies look brighter and bigger.
Yeah, that's the culprit.
But aren't black holes, famous for being totally invisible and just sucking in light? How does a black hole make a galaxy look brighter?
It sounds super counterintuitive, I know. But it's not the black hole itself that's glowing, it's the black hole's meal, basically.
It's meal, you mean the stuff falling into it?
Exactly. These particular supermassive black holes are rapidly consuming massive amounts of hydrogen gas.
Okay, so it's pulling gas in.
Yeah, but the gas doesn't just fall straight down. It swirls around it incredibly fast, forming what's called an accretion disk.
Like water circling a drain, but at, relativistic speeds.
Yes, moving so fast that all those gas particles are smashing into each other, and that immense friction generates intense, unbelievable amounts of heat and light.
Oh wow, so the friction from the gas is acting like a giant light bulb.
A cosmic floodlight, really. And here's where the illusion comes in. This extra light from the black hole's accretion disk mimics starlight perfectly to our telescopes.
Because astronomers normally estimate how massive a galaxy is just by measuring how bright it is, right?
Exactly. They assume all that light is coming from stars. So this extra glow totally tricks scientists into thinking there were just billions of additional stars that, frankly, didn't actually exist.
That is wild. So it's just a giant optical illusion throwing off the math.
Totally. And scientists actually gave these tricky little objects a nickname. They call them little red dots.
Little red dots.
Yeah.
Because they're small and, well, red.
Pretty much. They're compact because the light is all coming from the center where the black hole is, not spread out like a galaxy. And they're red because of how the light stretches as it travels across the universe.
Okay, so what happens when you account for these little red dots? Like if you mathematically remove that black hole glare from the data pool?
That's the best part. When you subtract that fake starlight, the remaining galaxies suddenly fit perfectly within the predictions of the standard model.
So the universe is safe. We don't have to rewrite all the physics textbooks just yet.
A standard model lives to see another day, yeah.
But, as is always the case with science, solving one mystery usually just uncovers another one.
It always does.
Because I noticed a really crucial detail from the source article. Even after they removed the little red dots, even after they fixed the math, the data still shows roughly twice as many massive galaxies in the early universe than the standard model expects.
Yeah, that's the lingering puzzle. It's not a universe-breaking crisis anymore, but it's still, a lot more massive galaxies than we thought should be there.
Right. Like, maybe we didn't find a skyscraper in the mud hut era, but we still found way more big stone houses than we expected.
That's a great analogy. And the proposed solution for this is actually really fascinating. It turns out the early universe was just an incredibly efficient star factory.
A star factory. Okay, how does that work? How is it more efficient?
Well, think about normal star formation today. You have a big cloud of cold gas. Gravity pulls it together, it condenses, and eventually ignites into a star.
Simple enough.
But the act of contracting actually causes heat, and when stars ignite, they push outward with stellar winds and radiation. That outward pressure blows the remaining gas away.
Oh, I see. So today, the universe has this built-in braking system. The gas pushes back, which stops more stars from forming.
Exactly. It slows the whole star-making process down to a crawl. Modern galaxies are actually pretty terrible at making stars efficiently.
But the early universe was different.
Very different. Because space has been expanding for billions of years, the early universe was much, much physically smaller, which means it was incredibly dense.
So everything was just packed tightly together.
Right. And because of that extreme ambient density, it was so much harder for that outward pressure from new stars to actually blow the surrounding gas away.
It's like cooking in a pressure cooker instead of just a normal pot on the stove, right?
That is exactly what it's like.
The incredibly dense environment of the early universe forced the recipe of star formation to happen at warp speed. The gas couldn't escape, so it just kept making stars.
Yes. The density essentially broke the braking system. It forced the stars to form much faster and in much greater numbers than they do today.
Man, that makes so much sense. So it completely explains why we're seeing these massive galaxies early on.
It really does. It ties the whole picture together beautifully.
So just to recap all of this for you listening, the standard model of cosmology is totally safe. We didn't break the universe.
Thankfully.
We just needed to, account for these hungry, glowing black holes masquerading as billions of stars. And on top of that, realize that the early universe was basically a high-density pressure cooker for making stars.
Yeah, and I think it's worth reflecting on a quote from Catherine Chorowski from the article. She said, "It'd be a terribly boring field if one paper figured everything out."
I love that quote. It's so true.
It really is. I mean, this whole deep dive is just a perfect real-time example of how science actually works in the real world.
Right, it's not just static facts in a book.
No, it's constantly questioning assumptions, finding new data with incredible tools like JWST, and then just refining our understanding of reality.
It's a constant evolution. And speaking of questioning things, I want to leave you, our listener, with one final, lingering thought to ponder on your own.
Oh, I like where this is going.
If the sheer density of the early universe acted like a cosmic pressure cooker, one that completely changed the speed and efficiency at which stars form, what other fundamental processes of physics might have operated at completely different, unimaginable speeds back then?
That is a wild thought.
Right. Like, what other crazy phenomena are just waiting to be unmasked by the Webb telescope? Because if star formation was that drastically altered, who knows what else was behaving totally differently? Something to think about.